Hey everybody, welcome to Lesson 13. We're going to cover a couple more study strategies, how to do puzzles and a one-pager, and then also I'm going to review physics to help you get ready for your Google Classroom quiz. First of all, we'll talk about some vocabulary puzzles. Last time we focused a whole lot on highlighting notes, making flashcards, and actually narrowing down that big vocabulary definition into something small and manageable and more easy to memorize. Now we're going to turn it into something a little more fun for those of you who are like, that was boring. I get it. It's still a vocabulary puzzle game and it's not the most exciting thing in the world, but it's a little more interactive than just flipping through some cards and trying to memorize the words on them. My first puzzle is very similar to something that Mr. Fan gives you. He gives you the little diamond-shaped things where you have to match them up. And really, all I do is just change the shape to make it easier for those of us who don't have that diamond-shaped template. So if all you have is a sheet of paper, great. Draw lines on it, turn it into a whole bunch of little boxes. You have the word, and then next to the word on the opposite box, you have the definition that matches that word. And then you cut them apart, you mix them up, and you try to see if you can match them together again. If you're one of those people where you're like, I'm not going to remember what the right answer is, then before you cut it apart, flip it over, write little numbers on the back so that they're in order so that you can check and make sure you got it correct. Another thing you can do with vocabulary is to do a kind of mix and match game. I usually do this in 3 matches. If you don't have the supplies or you're not very good at drawing, then just do the first 2. So I'll have a card that has the vocabulary word or the topic that I want to know. And then I'll have another card that has the definition or main ideas. And then I'll have another card that has a picture. Again, if you're worried that you're not going to be able to remember which one goes with what, then put little numbers on the back. So the word that matches the definition that matches the picture, you'd all put like little 1s on the back or AAA on the back so that whenever you flip them over to check to see if you got it correct, you know if it's actually right or not. Now, when you're putting those little keys on the back, make sure it's like lightly and in pencil or something so that you can't see through the card because, it's going to be really tempting to cheat if you write it with marker and you're like, I can kind of see through the paper. So here's a quick little example of one I have about earth science. And so I have plate tectonics as my word. I have the definition there in the middle, and then I have a little picture that matches it. All I did was take a Word document, I made a table with 3 columns and 4 rows, and I filled in column 1 is all my vocabulary words, column 2 is all my definitions and main ideas, and column 3 are all my pictures. Then I would cut those pieces apart, shake them up in a little bag, and then spread them out on the table to see if I can find the word, the definition, and the picture that match again. Alright, for you more creative people, we have a one-pager. And basically on your one-pager, what you're going to do is you're going to put all the information that you know about a topic on one page. It needs to fit on one page. You can't have several pages because then it's not a one-pager anymore. It is basically taking 10 or 15 pages of notes, left side pages, essential questions, and jamming it all together. It's nice if you can add a border and color code things. For example, every time you write about protons, you highlight it in yellow because protons are positive and yellow makes you think about sunshine and sunshine is positive. So make sure you have meaning behind the colors you choose, the symbols you choose, the patterns you choose when making your one-pager. Here's one I obviously didn't finish, but I started a chemistry one. And you can see in my border that I have a Rutherford diagram of an atom, and then I have different particular elements on the borders. I have organic elements on one, I have all the metalloids that touch the stair-steppy line on the other, and then I have the noble gases. You can see how I was going to split up my stuff. I have a spot for vocabulary, I have a spot for definitions, I have a spot where I was going to put some test questions in there. Here's a 6th grade one I did about metals, nonmetals, and metalloids. Again, notice the color stuff, right? Nonmetals are blue. Guess what? In my periodic table I have over there, what color is nonmetals? Oh look, they're colored blue. And then I have my metalloids in red, and I have my metals in yellow. And then where they overlap, it's like, wow, I know what primary colors and secondary colors are, because where the blue and the red overlap, now I have purple. I also have along the sides some definitions that may be a little more difficult, like conductor or ductile. And I used a whole bunch of symbols instead of words necessarily in the Venn diagram. This is another 6th grade one about density. And so I have the little, formula triangle with density, mass, and volume. In each section of the triangle, I have like explanations of what volume is, going around in little circles. I have a couple example problems of how to figure out things about it. And this 6th grade one you've already seen because it tells you about all the kingdoms, and I've already shown you that one. Here are the ones that you've seen this year, and I made new ones this year, and I left them blank as far as color goes so that you could go in and trace or highlight or add your own color to it if you wanted to do those. So those are my 2 new study strategies for this lesson. So let's get into our physics review. A lot of your physics stuff comes from 6th grade. So some of your 6th grade stuff, you need to remember potential and kinetic energy and how they change. You need to remember how to calculate average speed in a math word problem, and then how to graph motion, which includes distance on the y-axis and time on the x-axis. You need to be able to use that graph in order to calculate average speed. You're going to have to describe how energy transforms from one thing to the next. So like the classic example that I always use is a flashlight. Chemical energy is stored in the battery and it turns into electrical energy, and then it goes through the wires, and then it turns into light energy when it hits the light bulb. 8th grade stuff are balanced and unbalanced forces, and how unbalanced forces cause a change in speed and direction of an object. We differentiate between speed, velocity, and acceleration, and how to calculate each of those. We had Newton's 3 laws of motion, the law of inertia, the law of force and acceleration, and the law of action-reaction. In 6th grade, potential and kinetic energy. Potential energy is any energy that is stored. So the energy is not being used, the energy is kept and going to be released in some way. The most common example is gravitational potential energy. And so that's anything that is higher off the ground has more gravitational potential energy than something that is low to the ground. Other examples would be anything stored like the chemical energy in a battery, or if you stretch a rubber band or a spring. Kinetic energy is the energy of movement. So all that stored energy from potential is now being transferred into kinetic. Potential and kinetic are opposite. And so if an object is higher off the ground, it has more gravitational potential energy. But if that object has fallen, it is like just barely before it hits the ground, it is almost all kinetic energy. So your other examples would be when you let go of the spring, you let go of the rubber band, or you let go of the bow for the bow and arrow. Here's a little diagram of somebody with potential energy. The ball has potential energy because it's high up, and when they let go of the ball, that potential energy will transform into kinetic energy. That second picture, where the ball is halfway down, then it's half potential, half kinetic, and then if there were another picture of the ball right down there at the bottom, then it would be almost all kinetic and almost no potential. There's a little diagram of the roller coaster here where you can see how the potential and kinetic energy bars change based on the height of the roller coaster. So when it's at its highest point, then you have the highest amount of potential energy. When the roller coaster is at its low point, which is right there along the bottom, you notice the kinetic energy bar goes up right there. The other part of 6th grade you need to know is how to calculate average speed. Just like density, you need to know the formula. So let's do a practice problem. My formula is speed is equal to distance divided by time. I'm given a problem where I'm given 40 meters of distance was traveled, and it took 80 seconds for the person to get there. How fast was the person traveling? I would plug that into my formula. Speed is equal to 40 meters divided by 80 seconds. And so my final speed would be 0.5 meters per second. Please pay attention to the formula. Don't just automatically divide the bigger number by the smaller number, because if you had done that, they would have come up with a speed of 2 meters per second, which is wrong. For graphing motion, this type of graph should look a little familiar to you from 6th grade, and you basically need to describe what's happening. If a line is horizontal, that means the object is stopped. If there's a diagonal line, and on this one there's 2 different diagonal lines, then that means my object is moving at a constant speed. If the line is going up, that means the person or object is getting farther away from the starting point would be 0, and if the line is going down, then that means it's coming back and going closer to the starting point. You can use y and x in order to calculate speed. So on this particular graph, we start with a person who is walking away at a constant speed. They stop for a little while and they're not moving, and then they come back. And since the slope of that line coming back is a little steeper than the going away, that means they walked away slowly, stopped for a while, and came back very quickly. Every now and then you'll see a math problem that says, what was their average speed from 0 to 5 seconds? So you'd use your y and x values in order to calculate speed using the formula speed is equal to distance divided by time. And so looking at this graph, my distance between 0 and 5 seconds is 5 meters. It took 5 seconds to get there, so my total speed is 1 meter per second. The last 6th grade topic is energy transformations. So for energy transformations, it's kind of a two-part thing. 1, you need to know the different types of energy, and 2, you need to figure out how energy changes moving from one thing to the next. One type of energy is chemical energy, and that is the energy that's stored in batteries, food, gasoline, and coal, and that energy is released through chemical reactions. Mechanical energy involves anything that moves. So when the wind blows, when water flows, that would be mechanical energy. Mechanical energy is almost always used in engines and generators. There's always a part of a car engine or an electric generator that moves and spins in circles. That is most closely related to kinetic energy that we've already talked about. Electrical energy involves anything that uses power. It is the flow of electrons through a wire, and that flow of electrons is a type of energy. It's electricity. Thermal energy is heat. Heat is caused by the vibration of atoms. So if it's a solid, the atoms are vibrating a little bit. And the more they vibrate, the more heat they have. You learned in 6th grade that thermal energy moves from place to place through conduction, convection, or radiation. This year, we've talked about convection through convection currents in magma and in the atmosphere for wind and weather. And we've talked about radiation through the electromagnetic spectrum. Other kinds of energy would be light energy, sound energy, or nuclear energy. And here's our cute little picture that goes along with energy transformations. So the person on the bicycle has to eat. By chemically breaking down the ice cream, that gives the person stored energy that they can use to change into mechanical or motion energy. Radiation from the sun is trapped by the chloroplasts in the plant, and it is transferred into sugar. Sugar is a food, which stores as chemical energy. The chemical energy stored in gasoline is put into the car through the process of combustion. The car's engine causes the car to move. And then lastly on that little picture we have electrical energy, so by plugging in the stove, now when you turn on the stove, that electrical energy goes into the stove and causes the stove to heat up. Alright, so we're finally getting into 8th grade stuff with balanced and unbalanced forces. So, balanced forces. That means that the net force is 0. If I add up all the different vectors, all the different forces that are acting on that object, they're going to cancel each other out, and so it's going to be 0. That means every force on there has an equal and opposite force going the other direction. So if gravity is pulling down, the floor is pushing up. That means the object does not change its movement. So if all the forces are balanced, but the object was already moving at 30 miles an hour, it's going to continue moving at 30 miles an hour. If the object was still and sitting on a table, it's going to remain still and sitting on a table. Another way to phrase that is to say that the object has no acceleration. Unbalanced forces are basically the opposite of balanced forces. When I add up all those forces, it is not zero anymore. One of the forces is going to be bigger than the other ones, and that is going to make the object change its movement. So if there's a bigger force going right, now the object is going to move to the right. That is going to mean the object is going to accelerate in some way. Here's a little picture of some tug-of-war people. The top picture, they are balanced. We have 300 newtons going left, 300 newtons going right, and so when I have 300 minus 300, 0 newtons. Why do I subtract? Because they're going opposite directions. If they were going the same direction, I would add them. The little bottom picture, there's 400 newtons going left, 300 newtons going right. When I subtract those, now I have 100 newtons moving left. That is unbalanced. It's going to cause a change in movement, and so the people are going to move to the left. Alright, so we have our differences between speed, velocity, and acceleration. Speed, again, is calculated by speed equals distance divided by time. We calculate the average speed, not the instantaneous speed. That means the total distance divided by the total time. We can't calculate instantaneous speed without having some kind of speedometer. So like in a car, when it tells you you're going exactly 35 miles an hour right now, that's instantaneous speed. The official units for average speed is meters per second. Velocity is speed, but now we're adding a direction. So we've changed it into a vector, and we have to draw pictures of velocity using arrows now. The velocity will change if the speed or the direction changes. So if it speeds up, slows down, or changes direction, we have a change in velocity now, which is the definition of acceleration. That means we have a change in speed, a change in direction, or you can change both speed and direction. And that includes speeding up, slowing down, or changing direction, going faster, slower, left, right, up, down, any direction you can think of. That equals the change in velocity, and if you want to calculate acceleration, you would have velocity divided by time. Velocity has direction involved, so acceleration has direction involved also. Alrighty, our last part is Newton's laws. There are three major laws. There's the law of inertia, which means an object in motion stays in motion, or an object at rest stays at rest unless acted upon by an outside force. That object will stay still, or that object will keep moving forever in a straight line at the same speed until something changes how it's moving. On Earth, we constantly have air resistance, or air friction, and gravity. When you kick a ball in the air, immediately gravity starts pulling that ball down, air resistance slows the ball down, and so you have those outside forces acting on the ball that will keep it from staying in that straight line forever. Our next law is basically the math formula, force equals mass times acceleration. You're going to need to be able to calculate force, mass, and acceleration using this law. Generally speaking, if an object has more mass, that means there's less acceleration. If an object has less mass, then that means there's more acceleration. That's why whenever they do racing cars or racing horses or anything where they want speed, decrease the mass of the object that's moving. So race cars don't have passenger seats or back seats. And then if we relate mass and acceleration to force, then they match. So if we have more mass, we have more force. If we have less mass, we have less force. If we have more acceleration, we have more force. If we have less acceleration, we have less force. Lastly, we have the law of action-reaction. And so that means for every action, there's an equal and opposite reaction going in the other direction. In class, we had a couple examples. the boxer hitting the bag. When the boxer's glove hits the bag, the force of the hand on the bag is equal to the force of the bag on the hand. All right, there's an adorable little picture that kind of shows you your Newton's laws also. The kid is skateboarding. He's going to continue skateboarding forever until something stops him. Oh, look, there's a rock. And because the skateboard stops, the kid on the skateboard is still moving forward with the same speed and direction as he was before his skateboard hit the rock. The second law has the elephant there, and so because there's more mass on that elephant, that person's going to have to push with more force in order to get the cart to move. If there were a mouse on that cart, then the person would have to push with less force to get the cart to move. And our last picture shows for every action there's an equal and opposite reaction. So the force of the dog going to the left is equal to the force of the man pulling towards the right. So that is the end of lesson number 13. So your Google Classroom quiz is going to cover all that stuff about physics, and it's 10 questions. So I hope you're doing well, everybody. Stay safe. I'll see you next week for lesson 14, which is going to be our last lesson, and then you'll have just one more assignment before the end.